Finishing up section 6.3 on binomial and geometric random variables. After today's lesson, you should be able to calculate the probabilities involving geometric random variables. In a binomial setting, the number of trials is fixed, and the binomial random variable counts the number of successes. In other situations, sometimes our goal is to repeat a chance behavior until a success occurs. These situations are known as geometric settings. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials until a particular outcome occurs. Four conditions for a geometric setting are binary. The possible outcomes for each trial must be classified as a success or a failure. Independent. Trials are independent of one another. Trials. The goal is to count the number of trials until the first success. And S. Success. On each trial, the probability of success must be the same. You can see this is slightly different than it was for a binomial setting. If you can remember BITS, B-I-T-S, you can remember the four conditions for a geometric setting. Here's an example of a geometric setting. Let's say I'm flipping a coin and I want to find out the probability that the first head would not come up until the third flip. I have a binary setting. It's either going to be a head or a tail. Each coin flip would be independent of the other. The goal of this situation is to figure out the probability that the third flip would be the first head. And success on each trial is the same, 0.5. In a geometric setting, if we define the random variable to be the number of trials needed to get the first success, then y is called a geometric random variable. The probability distribution of y is called a geometric distribution. The number of trials y that it takes to get a success in a geometric setting is the geometric random variable. The probability distribution of y is the geometric distribution with parameters of p, the probability of success on any trial. The possible values of y are 1, 2, 3, and this would continue on forever. Note, like binomial random variables, it is important to be able to distinguish situations in which geometric distribution does and does not apply. Take a moment to pause the video, open your book to page 398, and read the activity on that page. In this example, the random variable of interest is y, which would equal the number of guesses it takes to correctly identify the birthday of one of your teacher's friends. What is the probability the first student guesses correctly, the second, the third, and what is the probability the kth student guesses correctly? First, I need to verify that this is a geometric random variable. So in checking, binary again, success is guessing correctly and failure guessing incorrectly. Independent, one student's guess should have no effect on the rest of the students' guesses. T, we are counting the number of trials until someone guesses correctly. S, on each probability, the probability is the same, which is 1 out of 7. So I'm going to calculate the probability of y equaling 1, y equaling 2, y equaling 3, and y equaling k. Y equal 1 means the first person would guess correctly. Well, there's a 1 in 7 chance of that happening. To calculate the probability that the second student would guess correctly, the first student would have to fail for that to happen, which there's a 6 in 7 chance of that happening, and then the second person would have to guess correctly, which would be 1 out of 7. So in multiplying 6 sevenths times 1 seventh, I get 0.1224. For the third person to guess correctly, the first two would have to miss, meaning a 6 in 7 chance of missing, and then the third person would guess correctly, which would be 1 in 7, which would be 0.1050. For the kth person, you should notice a pattern here. The pattern is you're going to have one success, and then you're going to have n minus 1 failures, and you need to multiply those together. So the geometric probability calculation, if y is a geometric distribution, probability of y equaling k will equal 1 minus the probability raised to the k minus 1 times the probability. 1 minus p is the probability of failure. In the previous case, that would be 6/7. And then p is the probability of success. The table below shows part of the probability distribution of y that we just looked at. We can't show the entire distribution because the number of trials it takes to get the first success could be incredibly large. In fact, it might go on forever. You can also see a picture of this distribution as well. If I take a look at the shape of this distribution, it's heavily skewed to the right. The center, for this example, the mean is approximately 7. We'd expect it to take on average 7 guesses to get our first success. The spread, the standard deviation, ends up being 6.48. If the class played a birthday game many times, the number of homework problems the students received would differ from 7 by an average of 6.48. In calculating the mean, if y is a random variable that's geometric, with a probability of p successes on each trial, then the mean, or expected count, will equal 1 divided by p. Summarizing section 6.3 on binomial and geometric random variables. Remember, a binomial setting consists of n trials of some chance process. You must check bins. The binomial coefficient counts the number of ways k successes can be arranged among n trials. Remember, that's written as n choose k, and it's equal to n factorial divided by k factorial times n minus k factorial. If x is a binomial distribution, with binomial probability of observing k successes is given by the formula below, where n is the number of trials, k is the successes that you're trying to count, p is the probability of success. The mean and standard deviation of a binomial random variable are calculated like this. Mu sub x is equal to n times p, and sigma sub x is equal to the square root of n times p times 1 minus p. The normal approximation to the binomial distributions says that if x is a count having a binomial distributions with parameter n and p, then when n is large, x is approximately normally distributed. We will use the normal approximations when n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 as well. A geometric setting consists of repeating the trials of some chance process, but this time we're interested in finding the number of trials till our first success. If y is a geometric distribution with probability success p, the possible values of y are going to be from 1, 2, 3, and so forth, and the probabilities that can be taken on are given by this formula. The probability of y equaling k would equal 1 minus p raised to the k minus 1 times p, and the mean of the expected value of a geometric random variable y is equal to 1 over p. This is the conclusion of section 6.3 on binomial and geometric random variables. In the next chapter, we'll take a look at doing sampling distributions.